Yeah, welcome to another lecture on functional electrical stimulation. And today's topic is how to shape the technical pulses to get the nerves excited, and what should we consider, or what boundary conditions should we meet here. So there are the usual suspects here as literature. There's another book that's a quite special one from Norris and Prachi. They have been working for 20 years in the medical device industry and tried to mold all their knowledge into one book, which is exciting for those who already know what they're talking about, and a bit annoying if you try to enter the field, because they give you detailed knowledge without giving you the big picture. Well, that's a bit tricky, but it's a good book on those things they experienced from the very beginnings to the point where things were then really running well. Unfortunately, or funnily, there's not much new stuff that came after 2010. So you can find then a lot of books on the signal processing side of brain-machine interfaces, and then of course a lot of AI dropped in with machine learning and whatever, but all the engineering side is relatively constant since that. That means it does not mean that everything is good, but focus is laid more on the signal processing, signal analysis side. So, and if you think that the second half of the room is much too dark, I'm happy if you switch on the light if you like. So, if not, I'm also happy. So what is the outline for today? It's about characteristic parameters, and I'm pretty sure you have them all in mind. I like to talk a little bit about a graph that gives us an idea how the pulse width and the pulse amplitude correlate to each other. That's the Chronoxy Rheobase graph, and some comparison about physiological and technical excitation. What is the same, what is different, and at the very end, a very long table giving you an idea where people already tried to stimulate the nerves. And this is not complete. This is just the old stuff taking from the textbook, and of course any new application comes with new boundary conditions, but they are not that different. So it's more to get an overview from clinical applications, and I'll comment on those that dropped out from clinical applications due to certain reasons that I also mentioned then. So, the stimulus pulse. This is the one you will find most often, and we have to take care of the parameters. It might happen that other persons use them in a different manner. And that means it's always good if you talk to somebody, yeah? Say you as an engineer and a person from the medical application, you're agreeing on certain parameters, then it's always good to draw the thing on a piece of paper or on your iPad or whatever thing, and ask them, do we understand the same? So amplitude, do you really mean that voltage or current going in one direction? That's your amplitude, right? And here it's the cathodic phase first. So we have an amplitude, we have a pulse width. And quite often you can agree on the amplitude, that the amplitude is the amplitude. There is sometimes a different way of using the pulse width in medicine. In medicine, they believe the pulse width might be the cathodic plus the anodic phase. This is what you have to ask then. For us, pulse width is the width of one pulse. This is important because we can probably vary the width of the other pulse, and then it would be good to know what time is where, right? So please, let's do it like that. So the pulse width is the width of one single pulse. We might have a delay in between the cathodic and the anodic pulse. And the funny thing is, there is a lot of knowledge that from the physiological side, it's really beneficial to have such a delay. And then it comes to the technical feasibility, and people say, oh, it's too complex here. I don't want to program another line for a microcontroller. We skip it. Yeah, so it's beneficial to have that delay to keep the excitation thresholds from the physiological side as low as possible, but it's a bit more complex to program that in a whatever pulse generator. We consider that we use charge balanced pulses. That would mean the area under the cathodic pulse should be equal to the area under the anodic pulse from the magnitude side. If it's a rectangular pulse, you can simplify the integral just by length times magnitude, and then you got that. So nothing, no rocket science, really simple things. When we have that, it might be that the charge is balanced, but that does not necessarily mean that physiology take it as balanced, since we have different excitation thresholds if we apply a cathodic pulse or an anodic pulse. So that balance is here purely from the engineering side. We are more or less all used to electronic components, and we take it for granted. If I have a capacitor or a resistor and I put something in and reverse polarity and apply it, that exactly the same happens. This is not true for electrochemistry. Depending how long something happens at a chemical surface, if you reverse that, the speed or the velocity about the processes, so the kinetics and might be different. That means you cannot transfer your knowledge by 100% to the world of electrochemistry. Meaning, if you would say, I'll push in 1 coulomb of charge and I draw out a coulomb of charge, everything is the same. Probably not. Yeah. We have to consider that for us, otherwise you would get crazy. If you consider all the details of fundamental science, but it's when it comes to very sophisticated control strategies, for example, to maintain charge balanced, that just counting the charge is not enough. You have to measure, and then you have to superimpose different things. So if you look in latest microelectronics design papers on stimulators, you find that they measure the charge, amplitude times time, but then they also measure, is the voltage really at zero, and if not, should I push more charge in? Can I do this in advance, that I kind of predict the charge that might be there? Or do I measure it afterwards as a correction measure? So there are many options that you can apply then if you take it really serious at the detail level. Yeah?
Why are we balancing the charge on the first place?
The idea is, when you remember the electrode electrochemistry, that you want to keep your electrodes into the water window. And if you apply a cathodic pulse, you get a potential. And if you reverse the potential, the idea is to reverse all the electrochemistry that has been happened. So you reverse the potential, and you reverse, let's say, when you imagine water molecules have stuck to the surface, that they go away again and you start with a pristine electrode for the next pulse. If you would not balance the charge, there might be something remaining there, putting you a little bit of bias voltage on top of that. And if you do that for several times, the bias voltage would go more and more in one direction. And then you could exceed the water window, and by that you would generate oxygen gas or hydrogen gas, depending in which direction you go. And that means that charge balance is a kind of measure to prevent corrosion and prevent that or ensures that you maintain inside the water window with that.
So we can change either the current or the timing of the pulse.
Right. And this is an exciting question. What should we change? The timing, so the magnitude or the timing? And this is a kind of a philosophical question when it comes to physiology. So what does that mean? Is it better to do one or the other? And I ask you for patience, because this is then subject of one of the following slides, what that means. So if we know that we need a magnitude and a certain time to get enough charge on site to elicit an action potential, we can use that in different manner. We can do it really straightforward, brute force, switch on, wait, switch off, wait, change polarity. So this is here the easiest one, symmetric pulse up and down without any delay. The second easiest one is cathodic phase, anodic phase, and then you wait. That means the repetition. Yeah? If you we haven't done that experiment yet, but you might know that if you carry something very heavy over a longer time, that your hand starts aching, and then you start to tremble. Yeah, that's due to fatigue. That means your fast fibers are gone. They need some rest. And this shows you that you have a certain excitation frequency, which is not the fastest possible, but somehow matched to your activity of the body, that you can save some energy somehow. And therefore it's good to make that stimulation pulse and wait until the next should come. And therefore you have that delay, and if you look from one stimulation pulse to the other stimulation pulse, you have a period when that occurs, and 1 over the period is then the repetition frequency that you have, as shown here in B, for example. And then you can include a delay if you like, or you can have a long anodic pulse with a low threshold that you said, oh, I don't want to excite anything, but I want to use that current pulse to pre-charge my interface layer of the electrode, and then I do the cathodic stimulation. And I mean, this is here, if you have hundreds of pulses, the question is, what come first? That's a kind of chicken and egg question, right? So is the cathodic pulse first and the anodic follows? Or is the anodic first and the cathodic follows? That's again a more philosophical question at the very end, right? Where you start thinking of your repetition frequency. Or you see that by having a sharp pulse, you might come into that anodic break excitation, that by switching off the current pulse, that you get an excitation under the counter electrode, and for that reason you might slowly decrease the anodic pulse here. This is shown as a straight line here, since all of these pulses are made with a digital control. This here is a beautiful exponential decay, and this is done in an analog circuitry where you have a capacitor that is charged first, and then the capacitor is discharged, and by that you get that exponential decay. This is nothing you should program in a digital way, because that exponential decay is nothing physiological, but it comes from the nature of a capacitor. You could do it if you have to program that in a digital manner. You could have a step function there, and this is as good as that exponential decay. The question always is, and yeah. Yes and no. The question is, where do we have the capacitor? So if you take the electrode in account, then we have the phase boundary with that capacitive behavior. But the question here is, if we separate the stimulus pulse generator from the electrode, do we have in the stimulus pulse generator the second phase over a capacitive discharge, or do we have a push-pull situation where we change polarity to do that? You're right. If we look on the big picture of the whole system, we always have those capacitive things there, but this is kind of separated and focused on the generation of the pulses here, that slide. And you had that question about length and magnitude, and this is not that easy one. So we always have to look. I try to explain you things based on models, and we try to explain our whole life and world based on models that we can observe, and then try to get a picture what happens there. And if we elicit an action potential in a nerve, we have to change the voltage of the outside of the membrane such that the nerve cell gets to that magic threshold and generates the action potential. And you can now either say, I need to change the voltage at the membrane, or you can say, I inject some charge, that the charge accumulation is equivalent to the voltage change due some ionic displacement current, or you say, I push some current in and the current results in some voltage drop that changes my membrane potential. But that always says we have a kind of magnitude and a kind of time, and that time times magnitude is a charge. And if we have the same charge, if we have a small magnitude and a large pulse width, or a short one and a high one, is this equivalent or not? And how can I describe that? You can imagine if you have that charge and you wait too long in a fluid environment, then the charge diffuses away and is probably no longer there where it should be. If we imagine charged particles as tiny little balls that diffuse somewhere. And this is what the Chronaxy Rio base graph is about. It tells us which pulse width do we need at which magnitude to elicit an action potential. So we have the current on the y-axis and the pulse width of the cathodic pulse on the x-axis. And the shorter the pulse is, the more magnitude do I need to elicit an action potential. And then I reduce the magnitude and increase the pulse width. And you can imagine that there is probably a certain point in time where the magnitude is so small that you can increase the pulse width, but it doesn't matter any longer because it's already so long that that part of the charge is going somewhere. And this gives either a 1 over x or an exponential function e to the minus of something. And I start with the exponential one here. We have that minimum asymptotic value, which is the threshold of excitation at very long pulses, and this is called the Rio base current. That means you do not get below that Rio base current to elicit action potentials, no matter how wide your pulses are. And then there's a definition that tells us if I take twice the Rio base current, I call this pulse width then the chronoxy, TC. And we see in one of the following slides that this makes sense for another reason. But these are the two parameters that we have. And depending on the nerve, remember please the model that we made out of nodes of Ranvier and unmyelinated nerve, that we have an internal resistivity, we have a capacitance of the node of Ranvier, and that this determines somehow how the excitation threshold is. That means this gives us an idea, if we do that line here, how the nerve works, that particular fiber. If you do not get the particular fiber, but you do experimental stimulation, 2 electrodes somewhere on the arm, you could also do that. You look or ask the person, when do you feel something? And you change magnitude and pulse width and note the numbers, and then you can draw that curve by that. If your nerve would get damaged, or you would come from thick, fast-conducting fibers to thin, slowly conducting fibers, you would see that curves go to the upper right, because you would need more charge to elicit an activation. And by that, this is a nice way of getting differential view on the setting. Unfortunately, this part of electrophysiology dropped out in general education of physicians. So if you are a neurologist or if you're working in neurosurgery and stimulation, you should know that. But your general practitioner did not get that at his or her education. So this is something where the engineers have to spread the word into the medical community about that. And you can do some modeling here, and you come to something that this is the threshold current is equal to the rheobase current plus chronoxy over time, or the exponential equation here. This is the current. We can also look at the charge. How much charge do I put in? Do I have to see if this was... No. How much charge do I have to put in? And if my pulse has no length, I times TPV, so the area under the curve is 0. And the larger my pulse get, the more charge I do. Since we have, if we talk about excitation, we need a certain charge, yeah? If we have no charge, we cannot elicit anything. That would mean the charge line here does not go through the 0, but needs a minimum amount of charge that excitation can take place. And the funny thing, the funny thing is if we consider the energy that this pulse has for excitation, the energy curve has a minimum. And this minimum is at the chronoxy. That would mean if you would like to stimulate energy efficient, which could be good, for example, for a wireless system that is, or a system that is driven by a battery, would be good to have the most energy efficient stimulation there, then it's clever to stimulate around the chronoxy. And they're depending on the application, on the site in the body, on the species that you use, that chronoxy varies a bit, but is roughly in between 70 and 150 microseconds. So our pulses are relatively short, which is good for electrochemistry if you stimulate only 150 microseconds. So there is nothing, let's say, that is long-term there. So, and then if you have that charge balance, you can probably minimize the side effects on electrode corrosion if you do it in a clever manner. If it comes to modeling, and a lot of modeling has been done over the decades, how to, if you want to model, if I have an electrode somewhere and I have my nerve somewhere else, what current would I need? How's the current distribution? Can I get selective stimulation somewhere? Then it's always good to model that, and there are two options. One is that exponential one that I introduced, that is according to Lapicque. So these equations are called the Lapicque equations. Sometimes people don't like logarithms and exponential functions, since this needs a bit more of calculation power. One could also use that 1 over x approach on the right-hand side. This is called the Weiss equations. And the question is, what is more accurate? There has been a paper in the late 1990s about that. L stands here for Lapicque, W stands for Weiss equation. There is a difference in there. The numbers look really serious here, but if you compare the graphs, I would say it's not that serious. Yeah, so you have differences in there, but if you would consider then the electrodes and the variability between today and tomorrow and patient A and patient B, all those variations would be much more severe than the deviations in between those two models. So I would say 1 over x is good enough for a first round of approximation there, to get an idea. Yes?
How do we actually arrive at the chronic C or the real value particularly?
Experimental.
So this is experimental data and we calculate.
Yeah. I haven't seen any theory where you can derive, let's say, by, don't know, the ideal ion concentration or something like that, this stuff. This is really an experimental description that can be used also in practice, but more on a qualitative level than on a quantitative one. So you could take the models for simulation on one hand side if you want to simulate something. On the practical side, you would do it more to understand, you know, if a patient comes in, you would be the whatever engineering support of a neurologist, or you have a joint project working on stimulation of paralyzed persons, and the paralyzed person would be recruited or comes in, says, hey, I heard you do electrical stimulation, can you give me some surface stimulation to gain grasp function again? I said, okay, well, and then they said, that spinal cord injury happened to me 15 years ago. And then you look on the arm, would say, oh, that looks very much atrophic, so there's not much muscle left. And you then do not know from that description and looking on the arm, is this really a spinal cord injury, or is there probably a damage on the peripheral nerve? Or is it both? You know, it could happen if you have a serious accident that it's not only the spinal cord, but on top of that, some damage on the peripheral nerve. And if you just use the phenomenology, one could say this is a flaccid paralysis because the arm hangs loose. Yeah, but it doesn't help. You don't know if the arm hangs loose, if you can stimulate it or not. If you would use then this method, and wobbling through amplitudes and pulse width and get the parameter, and you find your urea base and you calculate the Cronach C, and you would find your Cronach C value, let's say about 200, 250 microseconds. You would say, hey, look, this seems to be a spinal cord injury. We can try to train your muscles, and you might then have a carryover effect. Like you know from training, if you run and you don't run the other day, it still helps, yeah. And over the time, you get more trained. This is something you can do with such a paralysis. But if you would find that your chronoxy might be at 200 milliseconds. This is a clear indication that the peripheral nerve is damaged, that you need a huge amount of current, factor of 100 probably, to elicit the muscle. And in this case, you have nearly no carryover effect. That means what you don't see under the skin is not only a muscle with atrophy, but there has been then undergoing a complete reorganization, a lot of fatty tissue, different muscle fibers in there that are really hard to excite and do not show any carryover effect. That means if you stop stimulation for 2 days, all your efforts that you elicited are gone again. That was the result of a 10 years or 5 years project of several places in the world where they investigated that peripheral nerve damage and the influence of electrical stimulation on that. And that's really a sad story, because then it really does not help. And that's important. If you would have an injury where there's an option of nerve regrowth, so kind of regeneration, you would be able to see that, because the curve might be in the bad region, so upper right, but over time and over training and rehab, it might probably go back to the lower left. And then you would have a kind of qualitative measure to show, oh, this person is on a good way in nerve regeneration, for example. The reason why this method is not that popular is that it takes a lot of time and a lot of experience. So if you do that only once a year or once every 2 years, and it takes you 2 hours, then you are probably not that educated or trained in a right manner to find that out, and then you might choose the wrong parameters. And if you choose wrong parameters in spinal cord injury patients, that quite often lead to spastic attacks. So you elicit then spasticity, and people get a cramp and are worse than before. This is not a basic problem, but it's not a basic problem of the patient. It's sometimes a basic problem of the physician or the physiotherapist not knowing enough about electrical stimulation to apply that. And therefore, it's really hard to bring that into the broad practice, since it's a bit difficult to use. So you must know a lot of things about that to use it properly. A colleague of mine in Switzerland, in Swiss Paraplegic Center, is using that for years. But she says sometimes it takes you 2 years to train the muscles of spinal cord injured patients before you can really use functional programs to support grasping or things like that. So really tedious process where both sides, the physio side and the patient, must be really willing to go that long way. Here we have that all summarized in one graph. I stole the graphs from a German booklet for patients, and therefore there are quite a lot of inaccuracies that I did not overwrite, but just want to show you. So very important, if you talk with others and they talk about current and have a V as unit there, then it might not be current, right? Then it's probably voltage. So keep your eyes open. I think as engineers, we should be responsible to do it in the right manner and find out those tiny little things that might go wrong. But the general statement is the same. So if the muscle is denervated, that goes to the upper right. And as said before in that current charge energy graph, there's nothing like stimulation with zero charge. So we have here, that's hard to read, that should be the Rio base current times tau. That's the time constant of the nerve, 1 over RC. So that's the theory, right? You can also do that in practice. But if you want to go a bit deeper in the characterization of nerve excitation, we have to keep in mind that an electrode is not an ideal point source, but is sitting somewhere in space with a certain dimension, and that the nerve is also not an ideal point source, right? But we have a nerve here with different fascicles, and the fascicles have their nerve fibers, and the nerve fibers have also different thickness, so getting more and more complicated. And I have an electrode sitting somewhere, and I need a counter electrode here depicted as ground to close the electrical circuit. And you can imagine, if I like to elicit a nerve cell, an axon, this distance to that axon is different than this distance to another axon. And therefore, I would need a different excitation threshold for axon 1 than I would need for axon 2. And this is unfortunately not linear. And the more the distance is, the higher that is, and it goes with an exponent of 2. So we have the threshold current for the nearest axon, and imagine now they have all the same excitation threshold, same diameter, which is not true. But for simplicity reasons, just imagine that. And then we would have the real base current plus that K, that's the gradient, the inclination of the graph, times R square. So the further the whole story, the further apart the nerve fiber is, the more current I need. And if we now also look in the current diameter relationship, so that would mean we would have again our electrode, and we would have a nerve, and we have a fiber, and this is where the current goes. And imagine this would be a fiber and could be a thin fiber or a thicker fiber or a more thicker fiber, a more thick fiber, you know, then the thicker the fiber, the lower the excitation threshold is. But that's also not linear, that's non-linear, and goes with 1 over the square root of the diameter of the nerve. That means a thick, thick means the denominator is smaller, and then the add-on term is smaller than with a thin nerve fiber, where the denominator, a small number in the denominator gives a larger value, would be larger. And that shows you here, the smaller the fiber, the higher the threshold, the thicker the fiber, the lower the threshold. And if you would now overlay this graph with the graph from the previous slide, then it comes very clear that it's a nightmare to elicit thin fibers at a larger distance. Because then, and if you have thicker fibers in a smaller distance in the way, you will always get the thicker fibers that are close to the electrode before you get the thinner fibers that are at the larger distance there. And this is something that makes our life really complex and complicated, and therefore that question about selectivity, how do I get one fiber without getting the others, is topic of another lecture on the selectivity of stimulation then. But this is all based on these observations here. And also one important rule of thumb, the distance of the nodes of Ranvier depend on the thickness of the nerve fiber. Yeah, that is due to the internal resistance that we have and the decay. You have those slides, I think, in lecture 2 about the spatial decay constant of the internal nerve potential that we have between the nodes of Ranvier. So if we go then to nerve stimulation of a nerve that innervates a muscle. We want to have, if I grasp something, I want to have a smooth grasp, not a trembling. And that, on the other hand, I want to be energy efficient, that I don't burn too much energy when moving, when standing, when grasping something. And that means we come to trade-off. If I stimulate once, I'll get a twitch, like a tick that you sometimes probably have with the eyelid or something like that. Yeah? And if I would then take 2 stimulation pulses, it depends on the time that I use. If I have one and then wait for 10 seconds and do the second one, I see 2 actions. If they get closer, I might get a muscle activation, and you have that slide where you see the time frames of nerve action potential, then the muscle action potential and the muscle twitch. There are different time constants there. So a short nerve pulse gives a longer muscle action potential and delayed muscle activation from the force side. If I overlay that, I might have here the first twitch and here the second one and then the third. And if you just superimpose those things, you can get a higher basic force over those ripples of excitation, relaxation. If I go even faster with my nerve action potentials, one after the other, that goes higher and the ripples get less. And if I do it even faster, then the ripples disappear and I get a fully smooth contraction. This is also called a tetanic contraction. This is here, the upper row is a sketch, the lower row are real data, and if we look on the repetition frequency of stimulation, it's between 30 and 70 hertz where we get that smooth contraction there. And that's quite cool because, well, 30 times per second is, well, it's something, but it's not that much, right? And if you, I prefer to take 50, that's easier if I take 1 over 50, yeah? The period would be 20 milliseconds at 50 hertz. And that would mean for stimulation, if I go close to the chronoxy, let's say 200 microseconds, I would have the cathodic phase 200 microseconds. I could take the anodic phase 200 microseconds. That's 400 microseconds. With a 20 milliseconds period, that will mean that 19.6 milliseconds is the pause in between. I have my electronic circuit and the electrodes only active for 400 microseconds, while they are at rest for 19.6 milliseconds before the next pulse comes. And that's not too bad. From a lot of time that electrochemistry can balance out, that physiology can restore activity, things like that, right? So, if we are now already on the muscle level, we have to consider something that's called recruitment. Our body is not a digital system in a way that all of our muscles are either off or on. Yeah, you know that we can have a graded recruitment to control the force. yeah, and we have no force or a maximum level of force, and we can grade that in between. And sometimes we have parts of the body where we experience that we have not that much fine control. So, for example, if we take our gluteus maximus muscle, that's here the butt muscles, this is something where we don't have that much fine control. But we have a lot of fine control in our eye muscles, for example. We can, if we have eye movements or something like that. And this is cool because depending on the function that we need, we have a different complexity there. And that's again kind of simplified, yeah? If we don't need fine control of the gluteus maximus, why should we have 3 muscle fibers per nerve ending? If we don't need that, then we have probably 10,000 per nerve ending, and it's still good enough. Yeah, the nerve spreads off, but it's one nerve that passes its action potential, and then it goes to all the endings and activates what we need. And this is a bit shown here, so we might have large motor units, and the assembly where one nerve cell is split up into muscle fibers is called the motor unit. We can have medium-sized ones or small ones, and we can have ones where different different nerves somehow intermingle and mix a little bit here. Physiology is, of course, not that easy. That means we have some recurrent inhibition here or gating mechanisms. This is all very important, but not topic of that course here. So that's more towards neurophysiology than how to bring things together or to control systems or something like that. And this is nearly, I've forgotten that. There are different colors on the muscle fibers here. We have different types of muscle fibers that either work with oxidative mechanisms or with glycolytic mechanisms there. That means there might be a fast fatigue or a slow fatigue. So I can stand here for 2 hours and I don't mind. If I would here run for 2 hours, I would be completely exhausted. That means we have different muscle fibers that are in action for different purposes. And based on our training status, we can change that ratio of oxidative and of glycolytic muscle fibers. We can change the size of the muscle fibers and things like that. If subjects undergo spinal cord injury, the composition of muscle fibers also changes. That comes more in detail than in a lecture on fatigue and the muscle status that we have. Oops. So all the goal behind that is the development of graded excitation, so that we have really analog adaptation to the real world. And the control parameters that we can use from the technical side are the amplitude and the pulse width. And you know that amplitude and pulse width are somehow intercorrelated via the Chronaxy-Rio base graph, and the repetition frequency that gives us a kind of influence on the recruitment if there's a transition between nerve activity and muscle activity. If it's about hearing or vision or whatever stuff that is based only on the nerve excitation, then repetition frequency is not that much of a parameter on which we can tweak. If we want to get a graded recruitment and we leave out the repetition frequency for a while, we have amplitude and pulse width. And if we go to a certain threshold of a pulse, say we are now super threshold, we could then either increase the amplitude to get more fibers and keep the pulse width constant. That sounds quite intuitive, right? With all the equations that you've seen and the recruitment characteristics. But there's also the option, that's a kind of more old style version, that you keep the amplitude constant and vary the pulse width. By that you also change the charge under the curve, and you move on your Chronaxy Rio base curve. That also changes the recruitment characteristics during stimulation. There have been some groups who worked on that, so constant amplitude, change of pulse width, I believe due to better intuition with keeping the pulse width constant and varying the amplitude, more groups have taken that opportunity. But all in all, it's a kind of same idea behind that. And what you use depends on the application at the very end and on your colleagues and the availability of whatever technology. To better understand what we're doing with technical excitation, we should mirror different parameters or different mechanisms between the physiological activation and the technical activation of nerves. Because knowing that and comparing that helps us a bit better to understand where we have to tweak, where we might see side effects. So in physiology, if my brain activates my muscles, I have a kind of asynchronous excitation of motor units. That means my brain has a good command control and activates one part of the muscle and switches it off while the other part is activated. That helps to reduce the fatigue because you're not running at full power, but you somehow switch on, switch off certain muscle fibers, and then they can recover for a short period of time before they are reactivated, if I'm not at 100% of activation of everything. And it's asynchronous, that it's one after the other. If I stimulate, I don't have that option because I have that kind of clock underlying my stimulation pulses, and therefore I have synchronous activation of whatever I get. And this is a bit disadvantageous. That's like carrying a heavy suitcase. Then you have activated every fiber at the same time, and that promotes fatigue. In physiology, our brain activates the small fibers first to keep, for example, in stance here, a general posture in my legs. And if you would bump into me or I would walk and stumble, then my fast fibers are activated to as balance control. Knowing the excitation thresholds during electrical stimulation, we get that, unfortunately, the other way around. So we get the thick fibers first, that are the fast fibers, and the thin fibers second, the slow ones. And that is called inverse recruitment, because it's the other way around. And that causes, unfortunately, fatigue, those two things, synchronous activation and inverse recruitment, while our brain is doing that very efficiently and we normally get little fatigue. On top of that, our brain smoothly and automatically adjusts to the muscle's working point. So if we would get a little fatigue due to the response and all the perturbations and the sensory feedback of the body, the brain would notice that and increase the motor drive accordingly. Since we have force and stress sensors in the muscles and tendons, so really closed loop. If we do technical stimulation, we do it from somewhere and don't have the sensors in the loop. That means normally we do something like a program control, open loop. We look if it's good and then we stimulate, and if the parameters of the plant. So if the parameters of the plant change, we have to identify them and then to adapt. We can try to implement that closed loop stuff, but it's not automatically in there. This is something then that takes additional technical efforts. And coming with fatigue, we have to measure that and get an idea, and this is not that easy. Fatigue comes also later more in detail. Fatigue is not, the absence of fatigue does not mean that you are fully recovered. You know that if you do sports and you have certain interval programs where you should do something and then rest for a certain time, then do it again, you experience that you get more and more tired over the number of intervals you're doing. And that means the fatigue, that short-term effect is probably gone, but you get exhausted. So the system is not fully recovered over that. And this is also something we have to consider when taking that into account in electrical stimulation. So it looks like we are running in a lot of problems here from the understanding side and the adaptation side. And that's probably one of the reasons why this methodology and rehabilitation is not yet there where I would love to have it. It's very complex, and you would need the patience of the subjects who take that, the education and the patience of the persons who apply that. And it's sometimes a deep understanding is needed from physiology, electrochemistry, and electronics. And this is something that is good on the research side, and people might find it excited. But if you undergo an apprenticeship of 3 years and you're supposed to learn everything after 3 years on the theoretical and the practical side, it's probably too complex. Yeah, therefore we have to check that out. But people did so, right? So there are some products on the market that run well, that help patients. And the most famous one for electrically stimulating target tissue is probably the cardiac pacemaker, which is a thing on its own. And persons needing a cardiac pacemaker don't have much to decide. They can take a cardiac pacemaker and they survive, or they don't take a cardiac pacemaker and they die. That sounds a bit sarcastic, but it's an easy decision, right? If you have decision between life and death, it's easier than a decision on the quality of life. Do I want to have something that is hard to measure at 10% higher level? Yeah, so this is more difficult, and I think that is one of the reasons why the cardiac pacemaker is so successful, because that's really a life-saving device. This cardiac pacemaker runs, it's one of the few devices that runs since 1959 on a voltage-controlled version. So they don't have current control. They say voltage control is good enough for us. One of the reasons is you save one operational amplifier at the output if you take a current source instead of a voltage source instead of a current source. So it's easier to implement from the electronic side. And there are things where I would say it's easier to stimulate the structures in the heart than the structures in the nerves. Not saying that is easy going with a cardiac pacemaker, but it could be advantages there with respect to the complexity of the electronics, so we don't need it there. Since you might have seen that book that I recommend comes from 2005, and those guys have been 30 years on the job, means they grew up in the times where the cardiac pacemaker was brand new. And to those days, there were still some devices available where you glued electrodes on the chest to stimulate the heart. That sounds today completely ridiculous, because you undergo implantation and after 2 or 3 days you're fine again. You have to go through a rehab phase, but the system works beautiful as such. But remember, cardiac pacemaker was invented, first implantation was 1959, and then it took another 5, 6, 7 years before it really took off. And the first devices were really not at that quality level that we take nowadays for granted. There was something, a disease, that was called pacemaker dermatitis. And persons having a cardiac pacemaker got skin erosion where the pacemaker was. So the skin vanished. And the reason for that was that the first cardiac pacemakers were molded in hardware store epoxy. And that was not as biocompatible as it should have been. That means there was illusion of some toxic stuff out of that epoxy, and that killed the skin from the inside. And then materials have been covered around. So Parylene C was one of the materials where the epoxy-based pacemakers were covered with to prevent that illusion of toxic agents. And then after some years, all the industries switched to deep-drawn titanium packages that are completely non-toxic and biocompatible. And since then, pacemaker dermatitis has vanished as side effect, for example. But that was really those days, and therefore you find here some things that sounds nowadays a bit stupid, but I think it's important to remember that there have been those developments around. So, therefore we still have gelled skin electrodes here for cardiac pacing. If it goes to defibrillation, so heart arrest, and to reanimate the heart by an electric shock, we need much more energy and longer pulse durations. And that's amazing. While we're here in the cardiac pacemaker at the 200 microseconds capacitor discharge and up to 8 volts, we are in cardiac defibrillation here up to 40 amperes and 3 kilovolts. So you don't have to be afraid if you see those automatic external defibrillators where we have one hanging here. First of all, this guides you with an automated software which talks to you through the procedure. Second, you cannot do anything wrong, because if somebody is dead, that person cannot be worse than dead. Whatever you do, it can only get better. Yeah, that's important to know. That's why I'm getting completely mad when persons say, "Oh, this guy broke 2 ribs during reanimation." Yeah, you're dead. What is 2 broken ribs versus dead, right? So don't be shy. It can only get better. I mean, if the person is still talking with you and you want to defibrillate him or her, then you should think twice. But otherwise, it cannot get worse than being dead, right? So one really crazy thing. I'm old enough that I still know persons who worked on that. Is cardiomyoplasty. I don't know, I think it's now 50 years ago that the first heart transplantation took place in southern Africa by Christophe Bernard, or Christian Bernard. It's not that long, I've seen a news recently. And still, if you need, there's a lack of donator hearts for persons who desperately need a new heart. And suffer from heart weakness or heart failure. And these artificial heart-lung systems that you might have heard about during COVID for the really early severe cases are not working that well for a longer time, those heart-lung assist machines. And they're really heavy stuff. So there are ventricular assist devices that mechanically assist a weakened heart, mainly to get you alive until a donor heart is available. And in that context, when the ventricular assist devices were neither small, not working well, in the 70s, 80s, 90s of the last century, the idea came, can't we use electrical stimulation and a muscle that we do not need that much if it really comes to that hard point, to support the function of the heart. And one muscle, if you're really in a bad condition that we probably can agree that we do not need that much, is the trapezius muscle over the shoulder, where we normally lift the arm. So if you have the choice of either being a bit limited in arm movement or to die, we can probably agree that it could be alrightish to move to lose a bit that arm movement. And the idea was to cut the trapezius muscle, to pull it through the clavicle, and to wrap it around the heart. And then you take electrical stimulation to stimulate the trapezius muscle such that it presses out the heart. That's not ideal, and you will never get a marathon runner with that, but it's good if you have severe heart disease to survive. That was the idea. One group that was very far was a group in Vienna, at the Medical University in Vienna, which was a center of electrical stimulation worldwide until the 1990s. They are still good at that, but the boss retired, and there were some political decisions to fill that position in with somebody from imaging and no longer with electrical stimulation. And that is a really cool application. I followed all the papers in those days. That was their papers about success came out when I started my PhD on electrode development and stimulation. And then the paper stopped. And I did not find any report. And I was brave enough then 20 years later to ask that guy who worked on that over a bottle of wine, Wilfried, tell me the secret story. Why did you stop with that? And that was really not that nice one. That we were then at a point where we had optimized the operational procedure to get really the muscle nicely fit, and they worked on sheep. And to stimulate, and we got electrodes that did not break in that muscle, and we got a stimulator that worked over the years, and yeah, really stupid stuff. After a certain period of time, the muscle calcified. That means you have a muscle that's wrapped around the heart, you stimulate that, and the muscle gets stiff. And then the force development, of course, is going down, and it's vain. Yeah, you cannot use that. Luckily, parallel to that, the miniaturization technologies came up, and ventricular assist devices are now like a fist size, probably. They're still, to my knowledge, not fully implantable. There are one or two companies who are working towards that fully implantable artificial heart, but it's still a long way to go and a hard job to make that work. And that was one of those things that were then stopped because other technology overtook it, and it was better to use. Electroventilation was another of those stories that is a very successful one if patients use it, but there's only one company left who sells the devices, since anesthesiologists are really good in putting tubes into our windpipe, and they're good in controlling ventilation, and they're not that good in electrical engineering. Since the ventilation machines shrunk down dramatically, you get one that are now like a shoebox, yeah, and they can be easily put at the backrest of a wheelchair, because we are talking here of patients who have a spinal cord injury at C3. That means they cannot move anything. They are heavily in need of a stable wheelchair, and you can perform a tracheostomy and connect that ventilation machine. On the other hand, that electroventilation is something where you can stimulate the phrenic nerve in a manner that you stimulate subsections of the phrenic nerve, and you can thereby contract your diaphragm and have a natural breathing by that. has to work 24/7, so cannot stop breathing overnight or whatever. And I was lucky enough to experience one of those patients or subjects who had such an implant and was keen on communicating with both the general public and the scientific community. And that amazing guy was able to, and these stimulators are all fixed frequency. So you get 8 ventilations per minute or 10 or something like that. And when I'm talking, my brain matches my breathing rhythm with the length of my sentence, that I breathe when I have a logical break in my sentence. And this guy was able to adapt his speech to the fixed frequency of that implant. That was really impressive. Unfortunately, I have to say this was always under dispute, that application, since people said, yeah, you know, but does it really work? Is this reliable enough? And since the ventilation machines get smaller and smaller, most persons are now in favor of that hyper pressure ventilation. There are rare studies 10 years ago that showed that it could be beneficial to have electrical stimulation of that, but for market reasons also the number of spinal cord injured patients at C3 is relatively low. And the main reason for that is if you have an accident like that, it's very probable that you die before you get support. Therefore, the market size is so small that this is not really a business model for companies. While ventilation systems, due to all surgical interventions that are taking place on a daily basis, are around, and therefore people can also offer small ones. Yeah, and the rest here is something you can read on yourself. It's just an overview of these different things. Peripheral nerve stimulation, brain and spinal cord stimulation, pain relief, vagus nerve stimulation. We see that we have always similar pulse widths. There's a wild mixture between current or voltage stimulation. It depends on the companies if they believe in one or the other. And it's on us engineers to drive that. If you go towards miniaturization, current controlled stimulation is safer with respect to the electrochemistry and associated with that than with the risk of using something like that. And in some cases, it took years, decades, generations to believe that this electrochemistry and its observation is important. Cochlear implants currently start on that, so there is, of course, investigation before putting something on the market to do that, but there's then a certain safety limits and there are recommendations, and sometimes surgeons or medical doctors tweak a little bit at the boundaries. And has recently some publications came out from the first long-term observations. That means 25 years of cochlear implants being implanted. That one should consider corrosion there carefully. The good thing is this material in cochlear implants is still relatively thick, so we have metal rings of about 50 to 100 microns thickness. That means there's some material there. If you would imagine thin films with 200 nanometers or 300 nanometers, there are orders of magnitude in between. But there is corrosion under stimulation, and online monitoring would be beneficial really to get to stay in the safe side, in the safe region, and to prevent uh, corrosion where it's not necessary. And the reason for that is that you could say, why can't we test that? The thing is that all of those boundary conditions slightly vary depending on the environment inside the body. So if we have an inflammation, the pH value shifts. If we have a certain disease, the composition of the ions can change slightly, and that all influences then certain safe windows in which we can operate. We can be very conservative, always take a factor of 10 safety margin from each and every site, but then the area in which we can work gets smaller and smaller. So it's always that risk-benefit ratio that needs to be carefully assessed there. One thing I want to comment on, because that is sometimes not considered correctly. When you remember the electrochemistry, I always talked about that water window. That is 1.2, 1.4, however you calculate that volts. And we're now looking here at devices that are working in the tens to the hundreds of volt range. And that's correct. So we have to consider that we have an ohmic voltage drop over tissue. That means where the water window is at the electrode. We have the electrode with its water window, and then we have whatever is in between, fatty tissue, muscle, bones. And we have, when a current flows, an ohmic drop over that tissue that needs to be driven from the pulse generator. And if the pulse generator is only able to drive 2 volts, we cannot push the current through a tissue where the voltage drop would be 8 volts. Yeah, then we would come into saturation and we can no longer deliver the current that we intend to deliver. That is the reason why we have those relatively high voltage. For me, 10 volts is already high voltage. Same with the frequencies. Everything beyond 10 kilohertz is for me high frequency, whereas other persons here are on campus where everything between 1 gigahertz is DC. Yeah, so it depends always on the sub-discipline and on the application there. Therefore, it's good to check that out. Yeah, this is just a summary for you. There are many applications. Those applications will pop up. They will vanish again if they are not good enough for the application. And the reason why this is here is just to give you an overview of what is there. I find that gastric pacing extremely exciting. If you have motility disorders in the guts, in the intestine, you can also use electrical stimulation, but this is one of the fields that's still under research, and a lot of things are completely unknown, and there are certain periods of time where topic is very fashion, and then a lot of researches, because if it's fashion, you get research money for that, so you can work on that relatively easy. And then if the money goes away, a lot of persons go to other topics where the money comes, right? And there are others who continuously work on those topics. And we have to see what comes next. I've no idea. Yeah, so there's always an up and down in the applications here. I think it's important to look on the long-term run and to find out that more and more applications have become standard in clinical practice, which is good. And now we have to see what the next steps are, what the next applications are that enter broad fields there. And there's always a bit luck with that, yeah, that you have the right point in time, the right results, and the right spirit around, beyond the good results that you need. Yeah, some more, just for you, that you don't have to look up too many books here. And with this overview and some comments, I want to close. if you find by browsing through the slides something where you say, well, what the heck is that? Just ask me. I'm always happy to give you some additional information on that. As summary and learning targets, so you should know the parameters of a stimulation pulse and discuss a little bit what does that mean, how is it named, how can I tweak around a little bit. Chronaxy Rheobase graph, so what is that good for? What do I see, what don't I see? And what are differences in physiological and technical excitation characteristics, and a rough over-the-thumb range of values for the applications, that you're not completely in the wrong parameter space if it comes to that. With that, I'm at the end for today. I know that many of you tend to leave early for the Christmas break. I got an additional appointment next week earlier than expected from the university leadership. So therefore, I like to change the program a little bit in our course topics. Originally, it would have been selective stimulation. I would love to shift that into the next year, since I could ask somebody else to give that lecture, but selective stimulation is one of my favorites, so I definitely have to do it by myself. But I would suggest that we bring that first year lecture to this year, so the stimulation stuff. You might have, if you say, oh, I have already booked my flights, probably I'll bring the stimulators a second time with me, but the plan is to bring stimulators with me next time, surface stimulation, one-channel stimulators, and then we can here try out how it feels to stimulate hands and arms, how good that works, something like that. So an idea that you can try that out. Hand and arm always works easy. If somebody is in favor of baggy pants, baggy trousers, you're welcome. Then we can also stimulate the peroneal nerve at the knee. That gives foot movement. I'm pretty sure I will not do that next week due to the temperatures outside, to come with short trousers or something like that here. So we probably stick to the hand next week. With that, I want to close. Thank you very much. Nice to have you here. For those of you who leave, wish you all the best for this year. Merry Christmas for those who celebrate that, and a Happy New Year to all of you. And the Happy New Year then goes again to the remaining ones next week. So thank you very much, and bye-bye.